Let me start this by just introducing the panel, the 2014 Breakthrough Physics Prize winners, Brian Schmidt, Saul Perlmutter, and Adam Riess. And our moderator, following the tradition that was started last year, is the founder of the Breakthrough Physics Prize Foundation, Yuri Milner. Thank you.
So 30 years ago, when I was doing theoretical physics, I could get by with quantum field theory, but the last 30 years in finance completely annihilated my skills. So the conversation is going to be a little bit philosophical, if you can forgive me for that. So I guess the first question I wanted to ask to all of you is, what happened since 1998 in terms of specifically this discovery? Were there any additional measurements done and any interesting things happened sort of in the last 15 years? So Adam, maybe you'll start.
Well, so we saw the universe obviously accelerating, but it could have been the case that when we measured the equation of state, the ratio of the pressure to the energy density, it could have been anything less than minus a third, including a cosmological constant at -1. And so we could have right from the beginning or shortly after ruled out a cosmological constant. It could have been minus 2/3. It could have been a topological defect related to, 2 dimensions, domain walls. It could have been, some other value. We have now more or less measured it to be the cosmological constant to, 6 or 7%. So there was a lot of room in there for alternatives, and none of that room was the right answer. Now, I can't say what will happen the next time we squeeze down by that factor, but what we would say now that we wouldn't have said in 1998 is, it looks a lot like a cosmological constant.
Yeah. So?
Maybe even just stepping back a little before that is the fact that there was still, right in 98, we had 2 teams that were getting the result, but that was only one technique. And we, at that point, still needed confirmation from other techniques. And by now, there have been, even without the supernova result, I think you would still, at this point, believe that that we're seeing a accelerating universe. And that's the most immediate result that came in was about in the year 2000, I guess it was. The cosmic microwave background measurements reached a level of precision from 2 balloon experiments, the Boomerang and Maxima, that was good enough that you could see that the universe curvature, the overall curvature of space, was flat enough so that it made it very, very difficult for the result to be anything but the accelerating universe. So that was probably the first milestone. But then since then, there have been a number of other measurements that are getting agreement. Maybe the dramatic recent example is that we now finally have a second technique that can put a point on this expansion history plot. The baryon acoustic oscillation technique that we heard about a little bit earlier today has now put the first points that are non-supernova on that plot, and they agree very well, at least at the redshifts range where they overlap.
Right. So in addition, the fundamental thing is we actually know we're right. 1998, we're all going, this is really crazy, but it's what the data says. We have improved the precision, and the precision is very good, but we've also been able to start looking experimentally slightly different a field. So one of the interesting measurements that I like is looking at the growth of structure from large-scale structure, where you can actually see the growth of structure obeying what you expect from a cosmological constant dominated universe. Now, the precision isn't great, but if it were some sort of gravity being tweaked or something, you might expect those measurements to differ from what we see. And the fact that they agree so well is, I think, telling us that it's probably not, some F of R theory that's fooling us and just somehow looks exactly like a cosmological constant. And those measurements will get better and better.
So the question I always wanted to ask, but didn't have a chance, is was it really such a shocking discovery, or there was some theoretical physicists who basically were kind of calling the cosmological constant before the experiment.
In a room full of theorists, of course, there'll be.
Raise your hand if you
didn't.
knew it was a cosmological constant in 1998. Go ahead. Okay, there were a couple.
Right.
Great, good.
Right. So, also, I mean, we were observers. So, we tend to sort of, we have an idea of what the prevailing wisdom is, and the prevailing wisdom was that it was not a cosmological constant, that, the mass density of the universe was either low or high. There was a strong theoretical preference for it to be high, but nobody had found that extra matter. We were going to go out to a larger scale, and so we were the last gasp hope for finding the missing matter that would fill out to give you, flat geometry, critical universe, and we found the opposite. So I can only tell you I was totally shocked. I mean, it was not at all.
Yeah, it was, from my perspective, crazy. There were some theorists who said, yeah, we knew it had to be there. But some of the theorists, when I talked to them, say, well, okay, we knew it had to be there, but I didn't believe it either. It just seemed, it was sort of a toy addition that really was messy and didn't really want to add to the universe. We all knew it fixed a lot of things, but that didn't help me. I said, well, it fixes a lot of things, but it's crazy. So I thought it was crazy.
But I also want to add, I would sort of say shame on us for accepting that there was really no good reason for it to be zero either. I mean, I think the theoretical challenge of explaining it really has not gotten harder or higher because we see acceleration, because we say, well, it should be this small value. That, as a theoretical problem, was totally out there, and for whatever reason, did not get as much attention as I think it could have until the observation. But it didn't have to be that way.
Yeah.
Although I assume that this was one of these cases where just, there's so many things in play that you tend to try to find, okay, well, let's do something that seems simple for the first round of cosmology. And in some sense, cosmology has advanced very fast. We've moved from a period in which you had to make all sorts of simplifications just to make some progress to a period in which I think you're willing to consider more complex arguments than in the past.
What is going on in experimental cosmology today? What are the interesting experiments that you would mention?
I think we've kind of entered a realm of cosmology, I would call it everything but the kitchen sink. We're really trying to measure everything we can because we've all now learned that it's really about complementarity of measurements. It's not, you're not going to have your one, crowbar skeleton key that's going to open the door. It's really going to be this combination of things because it's hard. And so, and we're no longer have so much pride that we think it has to be just this tool or that tool. So we're doing everything. I'm going back to measuring trigonometric parallax, which goes back to the Greeks, but I know a way to do it better with the Hubble Space Telescope now, so that's what I'm working on. All the tools are being tightened, I think.
And there aren't that many tools is the problem, right? We have, for this particular domain, there's 2 methods in play and another 2 waiting in the wings.
What are the 2 in play?
So the 2 in play right now are the supernova and the baryon acoustic oscillation that you heard about earlier. Maybe just for those who might be watching now for the first time, the supernova measurement, you use the brightness of supernova to tell you how far away something is, and then you measure its color to tell you how much the universe expanded since that time. So that's the simplest one to explain. The baryon acoustic oscillation, you're using essentially it's the distance scales that we see between the hot and cold spots and the glow left over from the Big Bang epoch. And those scales set the scales in which you'll see galaxies forming later in time. And so if you measure where all the galaxies are at any point in history, you can actually see that growth of the universe. So that's the other technique that's in play. The 2 that we're still waiting on right now there's one technique that will be using the bending of light by the mass of galaxies on the way to us. This is we call it weak lensing, for gravitational weak lensing effect. And that one we expect will help get at this question of whether or not there could be some gravity difference in Einstein's theory of general relativity that could be in play here. And then last, in fact, here at Stanford in particular, there's been really strong work on using the number counts of clusters, and understanding how that clustering is a good indicator of both of these effects as well, the expansion history and the growth of structure.
And I think we also need to point out the cosmic microwave background does, it's actually something that's sort of reaching what we can do with it at this point, but it provides this amazing anchor, and there are some degeneracies in terms of measuring the equation of state, but when you combine it to the other things we're doing, it really tightens things up. And it is the sort of exquisite experiment we have right now. But even that, we're pushing it. So when you look, for example, at the Planck results, and we had David Spergel here, and we had George Estafio here, they would argue about which one is right at this point. So we're getting to that point.
WMAP or Planck.
WMAP or Planck. We would be arguing about the details. And that's one of the problems. We're beginning to argue about the details in all of these experiments because it's systematic errors. And as an experimentalist, we're in the unknown territories. Right? We're not really sure what might be going wrong, but everything is right to the edge. It's really hard to know.
And that's the time when you really need Adam's point of, we have to use complementary techniques, because we need to see consistency between several techniques to trust it. There's a recent, for example, surprising result of very high redshift baryon acoustic oscillation measurement that this is last spring, which just wouldn't have fit at all with our current picture of cosmology. And everybody's assuming that there are lots of ways in which it was just an early effort at making that very first measurement. It'll probably go away. But it was a very good example that if we didn't have another way of seeing it go away, we definitely would need some other techniques to cross-compare to see whether anybody else agreed.
Brian, and what are the key experiments for the next 10, 20 years that are coming?
Well, there's a number. So they're going to be around baryon acoustic oscillations, which I think that's really the sledgehammer approach. I always like to say that it's so simple and so boring, nothing could possibly go wrong. You look at 20 million galaxies, you take a power spectrum, you look for lumps and bumps, and you've got your distances. And it's not really exciting astrophysics from my point of view, but it is a brilliant experiment because it's really hard to go wrong. You have
by the way, this is the one that we think there was something wrong at the very high redshift point.
To be clear, that's a very messy signal. That's not on galaxies. That's in. That could be a measurement issue, and it's only excluded at sort of 98% on a messy signal. So let's wait and see that.
Just a question about cosmology.
Fair enough. Supernovae will continue to play a role, although we're sort of out in front right now. We are definitely into the very small baby steps to make progress now, because just how bright objects are across the sky turns out to be very hard to measure better than 1%. Measuring a ruler on the sky, which baryon acoustic oscillations do, that's much easier. That's just an angle measurement. One's a brightness measurement. You got an atmosphere up there. Very challenging. And then we have weak lensing and cluster, which are these methods which look at how large-scale structure grows. And that turns out to be exponentially sensitive to essentially how dark energy is affecting the expansion of the universe. So in principle, you can make really good measurements. The challenge is exponentially sensitive to measurement means exponentially sensitive to systematic errors. And so I think we're probably looking at how that's going to turn out. And finally, we have tightening up. This is something Adam is the expert on, measuring the Hubble constant more and more accurately. That allows you to combine it with the cosmic microwave background and improve measurements that way.
Saul, and what about dark matter in the next sort of 10, 20 years? Anything planned?
So dark matter, of course, is a very different kind of beast to study in interesting ways. One is that we would love it if there was any way to get at dark energy locally. If you could actually go and build a detector and look for dark energy. And there's a few suggestions of crazy ideas for that, but nothing in play at the moment that is commonly accepted. Dark matter, however, depending on what mass ranges you look for and what kinds of dark matter you're trying, you can actually go out and build very large detectors, and those are in play. And I think there's now there's several generations about to come online, which will allow us to have another real look at this next bit of phase space of mass space. So that is exciting.
And what is the time frame for that?
Oh, it's within this next 10 years.
It's happening now.
Yeah. I mean, it's already in play.
No,
right?
the next generation.
Yep.
Oh, so the 1-ton xenon detectors are probably the next 5 years or so.
Yeah,
I think is the time frame.
Yeah, the 5 and then 10 for the next one after that. And then there's the indirect methods as well. You can actually look for dark matter annihilating out in maybe the cores of galaxies, and that so far has been the place where people have seen the most exciting hints that made them think that maybe we may be onto something. So far, again, we don't yet have anything that looks definitive. But dark matter, well, and then of course the accelerators have the chance of giving you hints as well. So there, at least, there's a number of different things that feel like very conventional physics, in play that we could actually hope one of them will find a trigger. Now we've been waiting for a while, so it's not no guarantees on that one either.
So Adam, what do you think about the latest unexpected results of the experiments that have been discussed so widely?
BICEP2?
BICEP2 is a good one.
BICEP2?
Yeah.
Sure.
Well, it's very exciting. I mean, we at some point expect to see this signal from the CMB of this very subtle polarization. But it turns out that, what's that quote about Einstein about he's subtle but not malicious? If he is malicious, it's by putting dust in the universe, because dust screws with all of our cosmological measurements. I always thought it was just the supernovae that we used to worry about dust. Now it turns out even the CMB observations worry about dust. Dust is...
BAOs are pretty clean on dust still.
Yeah,
that's
pretty
the
good.
That's one thing they really do get away with.
But anyway, BICEP was trying to make a very hard measurement. They did very state-of-the-art measurements, but they were just at one frequency, so you couldn't distinguish the spectrum that they were looking for, the cosmic spectrum versus a dust spectrum. But that's going to change rapidly. There's at least, BICEP is collecting data at another frequency, and then there are a number of CMB experiments that are measuring at multiple frequencies. So this dust issue is not going to stick with us. I don't make predictions usually, but I predict that in 2 or 3 years at the latest, we have a measurement of that signal that we believe that is dust insensitive.
What
Do you
result?
mean a measurement that you'll...
That we see the B modes of the polarization that gives the evidence as we understand it of inflation of gravity waves.
So you're thinking there's going to be a large value of R.
Yeah, I think the current experiments in the next 3 years probably get down to R of 0.1.
Yeah, but it may
That's large,
probably even better than that.
Yeah.
But, I think it really depends on what the value of R is.
Yeah, that's true.
But ultimately, if you really need to get down to, for example, you want us to measure R to 1 part in 10 to the 3 or even better, but then dust is going to become a problem again, because you just have to keep on getting at that dust and dust and dust. And
Physics, advanced in physics does depend a little bit on some lucky breaks.
Yeah.
Right? I mean, a few constants in the universe have to come out to be things that you can actually measure. And we seem to do well so far.
Yeah.
It would be great if the BICEP2 measurement is correct, because then it's really going to be easy to measure and characterize, and we'll be able to see exactly what inflation did as it was doing its thing back a long, long time ago. If it's really, really hard at a very low level, then the best thing we're going to get is, we think it's that measurement. So that's not going to be very satisfying at all. So let's hope that it's a large value.
What would you bet on?
I have a bet with a certain unnamed physicist that R will be less than 0.08, e.g. that the signal of BICEP2 is the dust, but I hope I'm wrong.
Saul, what would you bet on?
I think today, if you ask most people, and I think I just go along with the crowd on this one, I think the odds are better than not that this will be dust this time around. But of course, the reason that we hope that we're wrong is because this would be the first chance we have to look just a little bit before the screen of the CMB, and that's exactly the kind of thing we love. So if we get to play that game this time, or if we have to wait another few years for that next level of precision and we still get to play the game, I think we'll all feel really satisfied. I think that'll just be great.
What do you think?
My prediction? You know, I just am sympathetic to the BICEP2 guys because, you know, our result could have been dust. I mean, the exact signal that we saw, the exact signal we saw was that these new supernovae were really faint, and that could have been dust. Now, we did all the work we could to rule out dust, and it would have required a kind of exotic dust that nobody knew existed, a gray dust.
We did 2 frequencies, right?
Yeah,
Right.
we did do two. We did a first order correction for dust.
Right. And then, you know, over the years, we actually we went out to higher redshifts and verified that it didn't look like dust as you went further out. But nevertheless, you know, I'm hoping at least half the signal was real, so I'll say R.1.
Great.
Unscientific.
Perfect. Now, if you look back 50 years, what do you think would be the key experiments from your standpoint?
If I look
Back 50 years.
If I look back 50 years, what were the key experiments?
You got to start 1960.
Well, 1964 is a big year.
Well, you know, in cosmology, I mean, you go back 50 years, and who is it? Ned Wright used to like to say there's only about 2.5 facts in cosmology, right? I mean, the sky is dark at night is one of the most important ones.
For 2 reasons.
Which is remarkable, but you know, the detection of the cosmic microwave background, just the monopole, I mean, just the signal, and the expansion of the universe. I think that's 2.5. I guess the sky's dark at night is half a fact, but
Expansion of the universe goes probably more than 50.
yeah, that's right. Yeah, so that's it, which gave a lot of freedom to play for theorists.
But, I mean, you know, probably you'd have to throw in things like the basic composition of the universe, so the Big Bang nuclear synthesis, you know, story was just an amazing success of cosmology. So I think that one you might throw in the cosmology side as well. And you know, I think probably the fact that we infer dark matter, you know, started the ball rolling of realizing that, you know, isn't what you see is what you get. You know, it's there's room for, you know, for extra elements.
What
Yeah,
are
so I would say large-scale structure measurements, which really, you know, got that idea that there had to be something like cold dark matter out there. The fact that we saw evidence for dark matter in galaxies and clusters, and then eventually in the CMB. So that was the huge thing. So we've got the CMB, really big, Big Bang nucleosynthesis, which sort of confirmed that notion. Large-scale structure, and then I have to admit I've come a long ways on this, but that notion that something like, and I'm playing to my audience here, inflation is required. I have to admit, 1995, you asked me about inflation, now I'm convinced. And so that's something that has come a long ways. It was a toy model that explains some remarkable things about our universe in a way in advance that I think that's an achievement that is really quite remarkable.
Inflation?
Inflation, the notion of inflation.
Yeah, but that's not an experiment.
It's not an experiment, but it's the experiments that lead around to it. It's the idea around it, and the notion of flatness, the fact that we have close to a n=1 spectrum in the cosmic microwave background, and that's we see in the galaxies. So it's that whole range of experiments around that. So
in some sense, you should count the CMB, not just the discovery of the CMB, but then this very fine fitting of the CMB as maybe a whole separate experiment, a separate data point. Since
that's certainly one.
Because it gives us flatness, it gives us this n.
So continue to push on history. Who are your heroes, individuals? Let's say last century.
Yeah, last century. I like
experimentalist.
Okay. I like. I'm going to say an unusual one here. I'm going to say Henrietta Leavitt. Because she, back at the turn of the previous century, women could not get PhDs in astrophysics. So if they were really interested, they could work as data analysts. And most data analysts are just sort of told what to do and don't give a lot of thought. She actually made the crucial discovery herself in the data she was looking at. That,
she was at Harvard?
She was at Harvard, that's right, and she looked at all of these blinking stars that were all at the same distance away in the nearest galaxy, the Large Magellanic Cloud, and realized that there was a nice relationship between the period at which they blinked and how luminous they were, and that gave us a distance indicator that is still incredibly valuable today. So, not only did she do that, but I would say that was not in her job description.
Is it Cepheid?
Cepheid variables, that's right.
I think there's some obvious heroes, just intellectual style that come to mind, but that you think of people like Feynman.
1 second,
but
experimentalist.
But I was about to say not experimentalist, so I can't count that. But I think that for me, there's a whole tradition that came out of the particle physics world that I definitely look at as the heroes of developing an approach to how you think about statistical data, which has ended up becoming such a big part of cosmology, in the years afterwards. So, I saw it locally through a tradition that came from Louis Alvarez, for example. A difficult character in some ways. You certainly wouldn't want to be giving a talk like this with Louis sitting in the front row in most meetings. On the other hand, it was somebody who was really willing to say, if you need to learn an area to invent a new technique, you'll just go out and learn that area, and you'll dive right in. So there's that tradition, and then there's this tradition that grew out of I think it was the whole group around that time of particle physicists who really got to know how to tell when you're fooling yourself by seeing features that aren't there, and just statistical fluctuations, and how not to be so skeptical that you don't learn anything real that is there. And I think that was
who would be the name there?
So I think well, now I'm trying to think of I still associate it with the same groups, but there are so many people involved in that tradition. In particle physics, it's the same problem of trying to say who is the person who is responsible for the Higgs discovery. You immediately starting to identify.
Well,
let's
that we
say
already
3
know.
people,
We gave prizes to them.
Well, exactly. but there wasn't one. You gave even that one. You had
That's
to divide
already
up.
identified.
Exactly.
Tough question. I've decided to restrict myself to people who are not alive, so as not to hurt my friends. And it's someone who I admire for their intellectual prowess, which probably have to be Fritz Zwicky, who went through and was really way out in front of his time. I think he probably could have been a little bit more friendly to his comrades.
You also didn't want him in the audience.
Yeah, I probably would not have enjoyed sharing an
theoretician?
office with him. Pardon?
Wasn't he a theoretician?
Oh, he was more of an observer than a theoretician. He's the one who brought the Schmidt telescope, not named after me or any of my relatives, to California and did the first supernova searches. Okay. He looked for dark matter. He had the idea of neutron stars based on these explosions, and the list goes on and on and on.
No, what year was that, approximately?
Well, so the supernova stuff, I mean, the neutron stars like 1932 or something, right? So. And he did a lot of stuff in the early 30s, and his supernova search was the game in town through the 60s, and the first Hubble diagram was done not by him, but one of his assistants, Charlie Cowell, in 1967, I think, the year I was born. So,
just sneaking in under the 50-year gap.
So a lot of people in this room at least admit that there might be a possibility of the multiverse. And if that's the way nature goes, then is there any way to verify it experimentally? What do you think?
I mean, I'm not a good person to ask about, is there a way to falsify it? Because from what I've seen and understood of it, there is not a definitive way to falsify it. I mean, there are certain kinds of observations you could make that if you were lucky would question it. People tell me if we see the equation of state of dark energy is not -1, that's a real problem for the multiverse. On the other hand, there might not be a multiverse and the equation of state might be -1. So to me, that's not a good experiment as an experimentalist. So, I don't think so, but we'll see what these guys say.
So I've been talking about Riess and others about the question of, is it possible that along with making a theoretical post-diction of a value or a range for a value for the cosmological constant, that we could find some other parameter that we don't already know the answer to that is narrowed down by the multiverse, where you would say, if this is true for cosmological constant, then there's some parameter that we should be looking for. Now, so far, it doesn't sound like anybody's immediately, we should show of hands, but I don't think we're seeing people immediately with another parameter to measure yet. But that would be an example of something where if you were able to say, here's something else that the multiverse would predict, then I think that would be a way of building a little bit of confidence that this wasn't, it wasn't just a post-diction, but it was actually something that you gave a little more credence to.
So we did hear earlier today that positive curvature would not be good for the multiverse, at least in some version of it. So I think it's good to go out and measure curvature as best you can, and if it happens to be positive and you're sure it's positive, then you probably have learned something. But of course, it might be impossibly close to measure to being flat, or if it's negative curvature, then you probably learned something as well. My fear is it'll be like the dark energy equation of state and be unfortunately close to the number of 0 or -1 and doesn't then tell you much. But I would say if you measured positive curvature, that would be something that would be interesting.
I want to actually answer also with a question is, what are the prerequisites for using an anthropic argument? Because, I'll take, the most famous one. I mean, the 93 million miles between the Earth and the Sun, right? You'd be crazy to try to derive that from first principles. And we have a deep understanding that there's a distribution of stars, there's distributions of planets, there's distribution of separations. It's crucially important, the temperature for whether H2O will be in the water state. And so, I'm completely comfortable with the anthropic argument from that standpoint. Then it seems like when we start talking about the multiverse, it feels like we don't have those same prerequisites. We don't have the deep understanding of the potential for distributions, the certainty that different values are taken on by whether it's symmetry breaking or whatnot. I feel like it feels like it's so premature. It's like using the anthropic principle about the Earth-Sun distance like 500 years ago or something, before we knew there were lots of exoplanets, that we knew there were different distances. It just feels like we haven't done all the prereqs yet.
And do you think that cosmology will come to a point where the particle physics experimental right now is when you need a lot of dollars to build the next machine?
We're already there.
And from that standpoint, I can clearly see the time when the next machine in particle physics will just not get built. And that would be the end of the game. Especially if we don't explain, well enough why we need that, which is getting increasingly difficult. So, do you think that cosmology is kind of heading in the same direction in sort of the 20, 30, 40-year time frame?
I mean, it's certainly you have
From
the
that
danger.
standpoint, we're living in the golden age.
Yeah. And I'd say that right now, it doesn't feel like we're at limits of that kind yet, right? Because it feels like there's so many experiments you can do at a range of prices. Some of them are very expensive. There's the satellite project that many of us have been working on for dark energy, which is now in the $1.6 billion range. But there are other projects that are $2 million projects that could be very important to do. Some less. So I think there's still.
Is it like infinite number of those small projects, or you will exhaust them all in 20, 30, 40 years?
I think it really depends on what you want to measure. If you want to measure the equation of state parameter, we probably start getting hemmed in a little bit. But cosmology is more than just measuring a few numbers. It's about understanding the life history of the universe. Very, very rich. And so I feel pretty optimistic that we can do a bunch of interesting experiments while we're trying to look on these big numbers along the way. And as long as that's true, and I think it will be during our lifetime, we'll be okay. I think that the universe is very rich, and we just haven't really got too much into the detail yet. So there's a lot to do still.
I mean, even the big picture still feels like it's a little bit young. I mean, maybe it will turn out that we somehow got all the main pieces in place, but I don't think it's necessarily the way to bed. I think we still have a chance that we'll still be finding some interesting results, even on the big scale.
And Saul was trying to negotiate a discount on his $1.6 billion satellite last night with the person he was sitting next to. So this is a great event for that.
What would be one of those unexpected discoveries for you?
Oh, I mean, if there was a hint that that the dark energy was a dynamic thing, something that was changing in time, I think that would be explosive, right? That would it would just make a huge difference, because now you'd have to be thinking about a whole range of theories that I don't think anybody is currently feeling forced to work on at this stage.
But there's also, imagine there are particles that we don't know, then we can produce those energies in certain places within the universe. It might well be that you can start using astrophysics to, you want 100 TeV, no problem. I can find you 100 TeV in a relatively nearby pulsar probably, and we can start looking for signatures. There's all sorts of ranges of things. And then there's just, we do not understand right now how hydrogen became stars. Right? The first star, we don't understand that fundamental thing. And so, okay, is that cosmology? That's cosmology to me. Probably not cosmology to everyone in this room. But those are some of the questions we can ask along the way. And interestingly enough, the same techniques we do to measure the equation of state allow us to understand those questions as well.
There's this linkage between what we call cosmology all the way to astrophysics. I mean, we talk about dark matter, and we like to, people in this room mostly think about, the particles and detecting them individually. Well, part of the rich story is they're supposed to make these nests called halos that galaxies will be inside of, and we can look for evidence of that part of the story as well. And it's all about the whole thing fitting together. So I think, what makes this a rich area is you can do experiments on lots of different levels to check lots of different parts of the story, and it's all contributing to our ability to, ensure that the story's right.
And there could be surprises
in
those.
What would be the example of something unexpected for you?
Something unexpected.
He doesn't spin coke. He can.
This isn't even cosmology, but finding evidence of life in a nearby planet.
Okay.
That would be incredibly exciting.
Unexpected?
Yeah. I mean, just in terms of the numbers game, unfortunately, it's probably going to be far enough away and hard enough to see that it's going to be many, many decades from now that we would have a shot at that.
Well, the unexpected would be
the
Alpha Centaurus, which is the nearest one, and if you find it there, then
so the initial, I mean, this is the
we're
problem.
in bad shape.
We're detecting extrasolar planet, evidence of life. You could come up with missions that would only be able to probe the 10 nearest stars, and so you have to be lucky. But you might do that experiment, and you might get lucky. So that would be unexpected.
Do you think you can build the engine that would accelerate something to a fraction of the speed of light, like 10%?
He can't even change the oil on his car.
It's true.
Sorry, Adam.
That's right.
Neither can I.
No,
It was a good line, though.
Yeah.
No, I don't.
Okay, so the last question is, what are you working on right now?
This is something I can talk about. A lot of what we do in cosmology is actually figuring out how far away things are, because that's just about the hardest thing to figure out, and it's just about one of the most important parts. And I'm going back to measuring parallax, which is just, it's not even astrophysics, it's just math, it's just geometry. But it turns out stars and Cepheids are really far away, and the angles become very, very tiny and hard to measure. So I've been working on a new technique to observe with the Hubble Space Telescope. When you observe a field of stars, instead of just taking a static picture, you drift scan the telescope across the picture so that all the points turn into parallel lines of light. And your ability to measure the separation between lines is much greater than your ability to measure the separation between points, because there's thousands of pixels involved in the measurement. So we've been able to get more than an order of magnitude improvement in parallax measurements, which then goes into improving the Hubble constant and this whole dark energy story. So that's what I'm working on now.
Saul?
So I do have to change the oil in my car now that you mention it. The main thing that we're working on at the moment, well, a couple of things, but one is trying to take that supernova standard candle technique and see whether we can really improve the precision by not treating this general class of type 1a supernova as a single parameter family, but asking, can we recognize every individual difference so that we can use very like-to-like comparisons of supernova when we make distance measurements. This involved finding some 300 supernova that we've then measured as they brightened and fade away and get a spectrum of every point. It acts a bit of a CAT scan, because you see the outer layers first and inner and inner and inner. And we find that some supernova match each other at every point, all the way through that CAT scan, and others don't match very well at all, and that the ones that match seem to be a much better standard candle for each other than the ones that don't match. and that this also is very important for systematics control as you go further and further back in time, because you're able to compare. Ideally, if we get to do this at high redshift as well, you'll be able to compare ones and make sure that you're only using similar supernovae to each other and not allowing drifts of populations to fool you. Now, the other end of all this is that we have to build the instruments and the capabilities to do this at the high redshift end as well, and so that's the other part of the project.
Right.
So I'm doing a number of things, but probably most relevant to this audience is we're doing a survey of the southern sky. And this survey allows us to do several things, but one of the things is to provide a very precise photometric calibration of the southern sky, which will enable us to then pin nearby supernovae to the more distant supernovae. And so we're working with the Dark Energy Survey, which is a survey down in Chile. And the idea is to be able to line those two sets of data up to unprecedented precision so we can make the best possible measurement of what the equation of state parameter is with supernovae, limited by the systematic uncertainty in the photometric system. But the same survey allows us, for example, to find stars that have no iron in them. And so earlier this year, we discovered a star that had no iron, the first such star. And since the Big Bang, it had hydrogen, helium, a little bit of lithium. Finding a star with no iron means you are in one of the first generations of stars. Now, it turned out this did have a little bit of carbon and oxygen and calcium, which we think we understand. And so we're able to actually indirectly, through galactic archaeology, figure out what a star was 13.5 billion years ago. And that's the beginning of that, but we should be able to find hundreds of those things. And so eventually, with the James Webb Space Telescope, we'll be able to actually look at the stars that explode and get them both directions. And so that's sort of my goal for the next 5 years.
And if you did not live in Australia, would you be serving northern sky?
Well, the Sloan
that
Digital
was
Sky
done.
Survey already did that. So
Okay.
being in the southern sky was a good reason to do this. Unfortunately, my telescope in 2003 was destroyed by a fire. And so it takes time. Anyone out there wanting to build a telescope, my advice is let someone else build it. It's hard work building telescopes.
Do we have time for a few questions?
I'm scared.
Hi. Now, what's your favorite theory for how type 1a supernovas explode?
Ooh, we got 3 people here. You should get 3 answers. Well, I can start if you want.
Sure.
I see compelling evidence that they explode in multiple fashions, that they do not all come from the same channel. I think there is some pretty strong evidence that some of them are what we call the single degenerate channel. That's where you have a white dwarf that is near the Chandrasekhar limit of 1.38 solar masses, accretes mass and goes over. It may be rotating more quickly or something. And the reason I would say that is actually I have a postdoc who's a nuclear physicist, and those are the only way we know how to make the amount of manganese in the universe. And those are the only explosions that really produce the amount we need. So that argument, I think, is pretty strong that we need that channel. But we don't really have any direct evidence that that channel exists. Double degenerate mergers, that's 2 white dwarfs coming together. There seems to be reasons why we might think that occurs as well, just because we keep on looking at the sites of type 1a supernovae, and there's no junk around them. They're naked. There's no evidence of a star that's dumping material onto them. There are some other reasons that involve what's on the outside of them. It might be true. And it may well be that some of them explode in what we call a double detonation, where you blow up a layer of helium on the surface of the white dwarf, it pushes a pressure wave in, and that ignites the core, causing the object to detonate. And you say, well, why would they work as a distance indicator? And it turns out because a relatively spherical ball of nickel kind of looks like the same any way you look at it. And Bob Wagner, who was around probably here sometime, there we go, he does radiative transfer, and you can kind of relate that a big spherical ball of nickel sort of ends up looking the same, and there's, you know, it turns out there's a pattern. The more nickel, the brighter, and we sort of understand that. And maybe we're lucky it's so nice and neat, but I think that is probably a messy answer. but it seems to me what the evidence is pointing towards at this point.
Yeah, and I would tend to concur also. I mean, and in fact, there was just this, last year or so, there was a few moments where papers came out showing, this supernova must answer this question because clearly this one could not possibly be the other type. And then another paper will come out, with a good example of another supernova showing the opposite. And both ones were presented, perhaps as if to say, this is the story. But now I think it's likely to be multiple stories.
And it should be said that it's really hard to get enough type 1a supernovae. They're more frequent than you might otherwise expect. You really need to be able to make them almost any way you can imagine to get the numbers up.
More or less, I would agree with a lot of what Brian said, except, I would still use the word Chandrasekhar limit. And I think the Chandrasekhar limit is still important. I think it is still involved in why ultimately the thing explodes. And I think you get an incomplete explosion of something that's near the Chandrasekhar limit. And so as Brian said, you get of order a solar mass of nickel. And that is still a darn good distance indicator, even though there's, a need to do a little bit of correction depending on, how much nickel you actually get.
Juan, and may I ask you a question? Why are you asking this question? I mean, this is...
He wants it switched.
I'm getting a little nervous.
I'm getting nervous too.
Yeah. Now comes the...
Well, I guess this is a great distance indicator, and apparently there is no consensus on how they explode. So
and does it mean anything?
I mean, that's been the story since the very, very beginning, right? That it was always an empirical.
And I think it means what Saul said. Well, what Saul said too, which is that unfortunately there's no one cosmological tool that will ultimately satisfy because we can't go visit them and ensure we understand the physics of them well enough. So it is going to require multiple tools because there will always be the possibility that we've grossly misunderstood what this kind of supernova is or how it evolves or the demographics change. So we will need multiples, but
it's also the reason why we're doing these kinds of things where you want to match each one exactly to its twin as opposed to take them as a whole group for exactly this kind of reason, that you don't want to be in a position of having a group that used to have 45% of one technique, one way to get there and 35% of another and another bit left over, and then have it change as you go back in time. So you want to be able to keep track, in some
But
sense.
it is true, just to allay some concerns. If you take the average spectrum of objects at a redshift of 0.5, and you compare it to the average spectrum at a redshift of 0, those averages look more alike than individual supernovae do nearby. So,
right, so we're worrying,
the central limit there, it's working in our
right, and we're worrying now at the sort of sub% level, it's at this point for that kind of issue.
Yeah.
But whatever the answer is, does it challenge the results in any way?
It certainly doesn't change the 1998 results because that was a big signal.
Yeah.
But we all worry about now we're trying to measure 25, 100 times better, and at that level, it may.
Everything matters
Absolutely.
at that level. Yeah.
Okay. Any other questions? Yeah, please.
Just funny to hear this. This is kind of a progenitor of a big data science, right? Correlation matters, but we don't need to know why. It's just, right? We're just looking at it and so on. If people talking about this in the morning, breakfast session, maybe for application science, may go that direction. It's just correlation we know from the data.
It's easier.
I don't know.
It's easier to do a lot of things to the 95% level than to do any one thing to the 100% level. So I'd rather, take the combination of many things to the 95% level. That's how I'll get my confidence, not from being 100% confident about any one observable.
But there is an underlying reason why it works, which is you have spherical balls of nickel that we sort of know what the radiative transfer is, and they provide a good but not perfect standard candle that we can use.
And we do, we like the fact that we have theorist friends of all sorts who are helping push from the other side, because we really would like to get it, nailed to some real physical understanding also. So it's not, so we're not happy the way that a complete data science would be.
But application science could go that direction.
That's true.
Any questions? Yes.
Since we're approaching to the limits of distance measurement by observing supernova, why don't we also observe the neutrinos from the supernova. Now that we know that they have a small mass, so there will be a small arrival time difference, that may actually help us in pinpointing what the difference is.
Yeah, so we need to have the Earth, the entire Earth, become a giant Kamiokande, we'll call 3++ or something. So we've done this experiment in the case of supernova 1987A, and there was no obvious measurement of delay. The neutrino flux, it's just, they're hard to detect. And we honestly, even if we have another object within our galaxy, boy, we're going to really measure it well. But it doesn't help you as much as you like, because it turns out the shock wave inside the star takes a long time to get out. And so measuring the delta T is going to be really hard, because that takes 3 or 4 hours to get out. And we don't know how well, we don't know that very accurately. So it's a challenge.
Andre?
So do you know of any theoretical explanation of your discovery which would not involve the multiverse?
Wow, Adam.
Wait a second.
I mean,
We're here, there has to be a multiverse? I mean...
No, the question is that you got this, prizes and everything. You made the discovery, which I believe is one of the most stunning discoveries of the last 100 years, honestly. Okay? And then we need to have some theoretical explanation of it. And the only explanation which I am aware of is related to the multiverse, and you say, no, it's not a good explanation. So that's an interesting for me to know whether you have any alternative one.
How about God? Not that I'm religious, but I mean, as observers, we can always see out to the horizon, and there's a fair bit of speculation that we have to do beyond that. I don't know if anybody.
I mean, I think you're getting to the point. Is if you buy lock, stock, and barrel inflation, right? Then we sort of start getting into trouble. And so the answer is I don't know of any. I'm still trying to be convinced that a multiverse explains what we've seen. I guess is where I'm still at. I'm not saying it's ruled out. I'm just saying I'm trying to understand how unique the multiverse explanation is, and I don't know.
You're not asking the question.
Yes.
You see, the question was, everybody agrees that I think that many of us agree that the multiverse explanation is not perfect.
Yeah.
Because of the measure, because of whatever. Yes. The question is, are you aware of any other single explanation which you can give me? Because it is your result. You probably have heard about all kinds of explanations of your result. Do you have any other?
Andre, you already don't have microphone.
Andre does not need a microphone. Well, I think we have more experts in this room than us. Does anyone here have anyone want to posit a theory? I have people tell me all sorts of stuff, and it's very difficult to know how crazy some of this stuff is.
But I mean, for the three of us, I imagine we've been hearing nothing but people proposing theories that would explain it. I don't think that any of us feel that we've gotten one that we would say, oh, I like that one much better than the multiverse. Yeah. So I think maybe that's a little bit the answer to your question.
Okay.
Yeah.
Yeah. Raphael.
I guess, yes, it does. Sorry, I would just say we actually have to thank you for having at least one explanation for the cosmological constant. If you had somehow proven that it was 0, we'd be left with none whatsoever right now. That doesn't mean that that the multiverse is correct, of course. I don't think we should ever claim that. But we, before you made this measurement, if people assumed that lambda was 0, it was complete fantasy.
But we did that, right? I mean, before we made the measurement.
My elders may have.
Oh, okay.
Yes, please.
So I totally agree with all that's been said conservatively about the multiverse, but it seems to me there's at least a logical possibility for a test that's a little bit different from what you've been saying, which is there could be a theory which has, many predictions, one of which is a multiverse, but others of which are actually accessible within our horizon. Okay?
Yes.
So that is a logical possibility. Of course, I have in mind string theory in the landscape and the possibility that we might eventually get some sort of cosmological test that indicates string theory. and that we might develop confidence in our understanding of the theoretical string landscape. And under those conditions, it might become much more convincing.
No, absolutely.
Yeah, I think we agree. Yeah.
Well, I just want to conclude by mentioning that the prize was actually divided among 51 people.
Right.
So one of the few prizes that really got spread so widely. And I think there are some heroes that are not present now that needs to be recognized. But once again, congratulations with the prize, and thank you for doing this.